Hey, what's up guys? Nick White here. I do tech and coding stuff on Twitch and YouTube, and I have everything in the description you would need to learn about me, I feel like, so just check those out. I also do a lot of LeetCode problems, but I've been doing these, this is my second one now. This is the same day as my first one. I did one earlier, and then, I don't have to, it's like 9 p.m. I'm probably go to bed at like 10:30, 11, so I was like, oh, let's get another hour stream in on this astrophysics stuff. Maybe we can make it through some more tutorials here with Python. So we're still doing the LIGO data tutorials. Earlier we left off, we just did some intro stuff. I think we plotted a data file that we downloaded from LIGO, and we were learning about the metadata that's in it and the quality of the data and how there's flags and quality is stored in binary numbers, and how you have to be aware that you can't come to you have to be aware of which data you're using because some of them have bad quality. That's pretty much it, and we're on step 4 now. So using the example API, this tutorial picks up where step 3 left off. Step 3, we looked at how data quality information is stored at GWOSC file. Now you know the data quality information is stored. You might want to wrap some of the things you learned into a few handy functions. Load one data file as example. Download the example API. Okay. We can download. What do you want me to just save it as a file? Should have downloaded and place it in the same directory as your GWSC data file. Save link as. I don't really want to do that. Save as. What was it called? Read ligo.py. Yeah, let's save it in LIGO stuff. That's what we have. Okay, it should be saved now. We can get rid of this. Great, and let's go back. So save it in the same directory with your other data. In addition to reading HDF5 files in the example API, we will also read gravitational wave frame files, like those described in the frame library page. Create a new file called usereadligo.py. Okay, touch. Let's grab it right here. There we go. It's right here. Use readligo.py and drop the following code into it. So we'll import some libraries into this guy. To read in all the data from a single GWOSC data file, you can use the load data method. So hopefully this will work because a lot of this code is Python 2, but we're not using Python 2. We're using Python 3. So we have strain time, chain dict, rl.load data. Great, and we'll load it from that file we got earlier. Function load data returns the strain time series, the GPS time of each sample, strain time series, GPS time of each sample, and a dictionary of all the data quality flags in the file. As in the last step of this tutorial, each data quality channel in ChanDict is stored in a 1 Hz time series. GWSC data files contains gaps where strain is not available. The data flag at one time. To loop over the strain segments, we'll use this code apparently. ChanDict data. Okay, sure, whatever. If you're working with a large data set, a common use case is to start with a segment list, a list of GPS times when we're interested in making our analysis. The API provides support for creating segment lists, as well as reading in data from a given GPS segment. Okay, load data using segment lists. This method refers to get strains and get segs. Only works for data files that begin with GPS times which are integer multiples of 4096 seconds. Not true for releases of individual events. To load a single file, please see the example above. Let's download a few GWOSC data files, see how the API works. Go to the S5 data archive, choose the S5 data set and the H1 detector, enter the times these, click continue to see a list of 4 data files. Download all of them to the same directory. Once a data file is in, oh god, okay, let's just do what they say here. We're going to click this, we're going to click choose S5 dataset in the H1 detector, and we need these times. So this is 84265, 84267 1,000. This is 656,000. This is, okay, sure. These are GPS times. Okay, can we, how about this? Because I can't remember what it's saying to do. So let's do this, and then let's open this up here. So S5 data set, H1 detector. I'm guessing they're saying GPS times. Enter start and end times. Time series data. Yeah, this looks fine. Yeah, this looks fine to me. Let's hit continue. We got 4 data files, like they said. Files that are available from the S5 data set. Automatic download tutorial, the last column, the time beginning, automatic download tutorials, downloading many files. What's the issue here? Automatic download. In this tutorial, data, let's assume past time, we want to run a search on the event. Let's go to the archive section, more precise, terminal, see, drill deeper, bulk data form S5, putting it in, redirected, where you could single file, download this. You can get all the data files. Use the bulk data form for S5. I mean, I literally did that. How do I download them all? Well, we can do this. Obviously. These all have different names, I'm assuming. And then what we have to do is put each of them. I should really learn how to download all of them, but guess what? I'm not doing that right now. And this is going to take 4 minutes. What? I don't have time for that. Let me see. Downloads. Where are these downloading? Desktop. What is this? How do I get to downloads? White's MacBook Pro, users, Nick, downloads, here they are. There should be 4 though, shouldn't there? Oh, this one's done. So, give me a sec, we'll do this. Open this up. 1. And then these are still waiting. Okay. It looks like the same file name. Is it the same file name? No. E42, yeah, so different file names, okay. And then this one has the almost completed file download. Sorry that it takes forever. I don't know, I guess there's a lot of data. And then we can just check on this. What does this say? So we download all of these files. Click HDF5 to download all 4 data files. Save them in the same directory. Once the data files and these are in your working directory, the API will make it easy to construct segment lists and load data on demand. First, let's construct a segment list by representing data that passes the CBC low mass category 2 data quality flag. Okay. So I'm guessing we're using the same file here. We'll have start, stop, segment list, and then we still need these to be done. Okay, these are done now. 1, 2, oh, did that one go in there? 3. Okay, we have all of the files that we need. And now we can continue on our path to doing something random here, whatever this is. API will construct segment lists and load data on demand. First, let's construct a segment list representing the data that passes CBC low mass category 2 quality flags. We have the start and stop times that we put in to get this data. And then we have start, stop, high, flag, and then we pass in the flag that we want. This method must take in a flag, start and stop time, and then H1. Okay. Typing print seg list will show the GPS times. Okay, so do we even really need any of this? No, we don't need this right now. Let's do it. Print seg list. Seg list. Let's try running this. Okay, so if we do have a segment list here. Values not being used anymore, just like earlier. We were having trouble with that, but that doesn't matter to me, I guess. Print shows the GPS times of the science mode times for this data. So GPS times of science mode times for this data, whatever that means. You can get the same information by requesting segment lists from the timeline query forms. As an example of how to use segment lists to load only science mode data, we can plot these first few seconds of each segment. Using this apparently, so let's delete this line, put this here for begin, end, and seg list, strain, meta, DQ equals RL, get strain, beginning, end. So we load the data, we make a plot, plot.figure, TS equals meta DT, real time equals MP.arrange, 0, end begin, meta DT, plot, real time strain, sure, this is just plotting stuff. Okay, there we go. There's the plot that we were looking for. We got a plot of each of the data files that we downloaded, I'm thinking. Figure 1, Figure 2, or maybe just 2 of the data files. What is this? Since 842.65.6000, 842.65.8143. It looks like it did. It looks like it did all of them. I mean, all of them within these boundaries, maybe. Begin, end, and seg list. Yeah, I think it was within the boundary. It did all of the files within that boundary. Sure. Running this loop should make a figure for each good segment and plot the first few seconds. Strain data for each segment. In general, loop over a list of good segments is a convenient way to apply data quality information and analyze only the data you want. For more examples using the API, try help RL into the Python interpreter to look at the API example page. If you want, you can download the entire script for this tutorial along with the example API. You made it. This concludes the introductory tutorial on reading GWOSC data files. At this point, you should be ready to download and use the data files from the data and catalogs page. You may want to look up some other tutorials that specifies uses of GWOSC data. Okay, so we're done with these tutorials. Now we can go to the data and catalog page and we can do other stuff. So this is some data, LIGO data, data for events. So we're going to see event data, documentation notes, confidence detection, what is this? Strain data, marginal triggers, reading files, segments, data quality, calibration versions. Let's go back to tutorial, self-paced course on this, data analysis. Here, this is what we kind of want to look into. So, what is this? Run Azure, view. Maybe we should go through this. What is this? Workshop web course. These are materials covered from the data workshop, 5 hours of lecture, 10 to 30 hours of data analysis, programming exercise, people pursuing a graduate degree in physics, astronomy or whatever. That's not us, but screw it. Target learning objective related to gravitational wave data analysis, LIGO and Virgo. If you're not familiar with LIGO and Virgo, we could see this, that's fine. Introduction to Python, the Python tutorial, Google's Python class, frequency domain. If you're not familiar, we have Fourier series, Fourier transforms in 15 minutes. I don't know anything about those really. The LIGO detectors, this is just a lecture about the LIGO detectors. Accessing data. Sure. What is this? Yeah, whatever, that's fine. We don't need to watch this. We can read, guys. We don't need to watch videos. We can read. Introduction to GWPy. Oh my god, it's all freaking videos. We kind of do need to watch some of these then. I'm not sure if we do, but I'm pretty sure we do. Yeah, these look like good videos to watch if we want to get farther along in this more quickly. Is there any notes? Lecture videos, program, registration, transportation, lodging, location. What did I just get? I got a notification. This is just dumb notification. Okay. Software setup, download data. We know what that is. We know what this is. Working with data. Okay, here we go. Example API, working with segment lists. LSC software stack, frame reading. Lots of plot tutorials. So what is this? I don't think we did this one. Spectrographs. Lots of plots. This tutorial assumes you know how to use Python to read LIGO files. If you don't, you might want to look at the introduction, create a file called lots of plots, and add the following code. MLab module, function density, download first part of the tutorial, so you get the file name. Make some example plots. In the example, we use all this. Plot a time series. You can plot a time series data like this. Next, let's plotting the data in the Fourier domain using a fast Fourier transform, because GWOCS data has a great deal of excess noise at low frequency. Spectral leakage is often an issue. To mitigate this, we'll apply Blackman-Widow before taking the FFT. Yep. The vector return of frequency domain is complex. Let's just plot the magnitude of this vector. This isn't what we need. See the structure of a file, plot the data, find an in-spiral, searching for astrophysics, find an in-spiral, automated downloads. That's all there is? That's it? Okay, this one might be better. Oh, here we go. This is what we want, guys. This is good stuff. Here we go. This is the meat and potatoes. Here we go. Binary black hole signals and LIGO open data. Here's exactly what we want. I was confused. Welcome the IPython notebook or associated Python script LOSC event tutorial.py. We'll go through some typical signal processing tasks. String time series data associated with LIGO events. Data released from LIGO Open Science Center. So we find the events, view tutorials, a web page. For this, what is this? What we're on right now? Oh crap! Yep. Run this tutorial with Binder using the link on the tutorial page. Binder. All right. If you're running this tutorial on your own computer, see the download section below. This notebook works with NB format version 4. If you're running version 3, pick it up from the tutorial page after seeing the desired event name below. You can just run the full notebook. This tutorial is intended for education purposes. The code below shown here is not used to produce real results, papers published by the LIGO Scientific Collaboration. Instead, we rely on special purpose analysis software packages. For publicly available gravitational wave software analysis packages that are used to produce LIGO and Virgo collaboration papers, see here. Okay, we'll get those eventually. For technical notes on this tutorial, see here. Intro to signal processing. This tutorial assumes that you're comfortable with Python. It also assumes that you know about a bit about signal processing and digital time series data or want to learn. That's us. This includes power spectral densities, spectrograms, digital filtering, whitening, audio manipulation. This is a vast and complex set of topics, but we'll cover many of the basics in the tutorial. If you're a beginner, here are some resources from the web. Okay, crash course. Digital signal processing is a new technology that is rapidly developing. Basically, DSP is the representation of a signal by a sequence of numbers. That's what LIGO data is. The numbers can then be manipulated or changed by a computing process to change or extract information from the original signal. Often this includes extraction of noise, for example. Bandpass shaping is another possible change that can be made. In fact, Using DSP, we can even originate and create signal numbers in a sort of reverse process. One advantage of this is that there's no requirement of tuning a signal. Is now just a sequence of numbers from a computer. This makes DSP a very stable and flexible way of dealing with electronic signals. Simple, more, yeah. So we kind of learned what DSP is here. AD conversion, an input signal is first passed through a low-pass filter and then digitized with analog to digital converter. This is called sampling. Okay. Tiny separate samples are taken from the input analog signal to represent at that moment by a digital value. Higher sampling rate up to a point, better we can reconstruct the original signal. Okay. However, sampling rates too high complicates our hardware, causes a problem that isn't a good design practice. Comprehensive, yeah. Okay. DSP, breadth and depths of DSP, roots of DSP. This is a book. I don't know if we will need to read a digital signal processing book. Oh, I lost my page. I go grab it. Yeah, sure. Where were we? This was like what we wanted, right? Yeah. Hold on. Okay. Download the data, intro to signal processing. Coursera has a course on it, just a bunch of random crap. Spectral density, signal processing, spectrogram, and well, lots more on the web. Download the data from your computer with a Python installation if you're using a pre-configured setup. Binder if you don't have anything set up. Otherwise, to begin, you don't have to download or set anything up. Okay. You don't have to download or set up anything. Sure. Oh, otherwise, begin the necessary files by downloading zip. Okay. Let's download this. I was like, oh, sweet. No setup. Psych. Zip file contains these IPython notebook, LLC. I don't have IPython. I have Juniper, and I was contemplating getting IPython earlier, but I think you can use Juniper, can't you? Who knows? Okay, so now we have LLC event tutorial. Python code for reading LSC data files, read ligo.py. So I need this too. I guess. Let's put this in desktop right now. Okay, where did that go? Should be, where did it go? Where are you? Read ligo.py. What? Read ligo.py. Putting it on my desktop, and then it disappeared. Oh, here it is. Okay. We have that now, and the event data file sampled. Oh, it contains that. Oh my god, I'm so dumb. I don't read. Waveform templates, and a parameter file in JSON format. You will also need Python installation with a few packages. We have these, I think. For hints on software installation, you'll see this. Tutorial should work on Python 2.65, including Python 3 and recent versions of IPython. You might see warning or future warning messages which tend to be associated with different versions of Python, not in Py, but they can be ignored. Hopefully they can be ignored. Yeah, I mean, yeah, hopefully. File type means that the data are in this format. Yeah, we already got that. Okay, so GPS time is number of seconds. Yeah, okay, sure. Set the event name or choose the plot type. So let's open this project folder in Atom, I'm guessing. That's what we should be doing here. Maybe. We're not doing LIGO stuff anymore. We're actually doing LSC event tutorial, which has a bunch of crap. Okay. Tutorial should work with most binary black hole events. Default is no selection. You must select one to proceed. Okay, proceed. What file is this? Event name, GWS. Yeah, we just pick any of these events. Standard. Okay, where's the readligo.py? So let's see. We're at the top here. Import these. We have all these functions. These are just a bunch of functions. classes. Okay, it's just one function of classes. This is the tutorial. Oh, and then we get to pick one. Okay, so we use the one that they have by default because I don't really care. Standard Python numerical analysis imports. Is this what we already have? Yes. Okay. So I wonder if this will actually run. We're actually going to switch directories here. LOSC event tutorial. And then we're going to try to run, what file is this? LOSC event tutorial.py. From SciPy. Okay, we don't have SciPy. No module named SciPy, so we're going to have to grab SciPy. Damn it, I thought I had downloaded all of these earlier. So there we go. This looks pretty foolproof here. Let's try it. We can actually just do this. And then we'll rerun this. It might take a minute here. Oh god, not even a minute, like an hour. Not an hour, but like, you know, a while. However long it takes, it's going to be annoying, I'm pretty sure. Yeah, that's pretty slow. Looks like we're looking at like 5 minutes. Collect my empty water bottles. Let me show you how many empty water bottles I have here. Here's just some. Here's some more. It's 10, 11, 12, 13. This is all I do, dude. It's just, wait, 1, 2, 3, 4, 5, 6, 11, 12, 13. 5%. Yeah, that looks like it's about it. That's a lot, though. 13. Before I take them down and put them into like a recycling area. 13. Wow. Let's just look ahead and see what we can do while we're downloading SciPy. Standard Python numerical analysis imports. IPython magical low must be commented out in the .py file since it doesn't work here. It's not even in my file. I don't even see it. I mean, the percent maybe they didn't have. I mean, yeah, I don't know. That looks fine. It looks like it's not in my thing. Config, maybe let's look for this actually. Yeah, it's already commented out. So you might get a matplotlib warning here. We can ignore it. Read the event properties from a local JSON file. Download in advance. PHH events v3.json. And we already have that. That's great. So try events. You open the JSON file, and then we have an exception if we can't find it or something. Did the user select an event name? Try event name. Print, you must select an event name that is in the JSON file. Okay, that's an exception. Extract the parameters from the desired event. So we select an event, and then we get a bunch of stuff from the event. So we get the file name for the H1 data, the L1 data, file name for the template waveform, sampling rate, FS event, set the approximate event time setting. More like just getting, it looks like. Extract, yeah. Frequency band for bypassing signal. Okay. Reading parameters from this event. So yeah, you get all the parameters. You read in the data. We'll make use of the data, the waveform template as defined above. Yeah, this is all in here already, right? Let me look for this. Note that in general, LIGO strain time series data has gaps. What percent are we at? 18. With filled with nans, and the detectors are not taking valid science quality data. Analyzing these data requires user to loop over the segments and test the quality of the data. Yeah, we already did that. In this tutorial, for simplicity, we'll assume there's no data gaps. This will not work for all times. So you have to make sure that the quality of the data is good because of LIGO being a piece of crud. See the notes on the segments for details. First, look at the data from H1 and L1. This is stuff we already have in our file, I'm guessing. And we just look at it. Delta T5. Just a bunch of stuff. Making plots. If make plots. What's make plots though? It's not. It's probably somewhere declared somewhere. Then you plot the data of the events, and this is what we're going to end up getting apparently. That's pretty cool. And the data are. I can't wait to run this file in 75% more of time. Plot the amplitude and spectral density. Plotting these data in Fourier domain gives us an idea of the frequency content of the data. A way to visualize frequency content of the data is to plot the amplitude spectral density, ASD. The ASDs are square root of the power spectral densities. Are the square root of the power spectral densities, which are averages of the square of the fast Fourier transform. It's a lot of stuff of the data. We'll go over Fourier transforms in the next video. I think that's the next thing we have to do is go over these Fourier transforms and go over digital signal processing a little bit. So yeah, we'll have to do that next video. These are just, we beat the tutorials today pretty much, and downloaded a bunch of stuff, got our environment set up, and then we'll do DSP, some digital signal processing stuff next time. And then once we get pretty good at that, we'll probably have to do 2 hours at least of digital signal processing and learning about it. Then once we get good at that, I think we'll be able to kind of start messing around with the data. So they're an estimate of the strain equivalent noise of the detectors versus frequency, which limit the ability of the detectors to identify gravitational wave signals. They are in units of strain, RT hertz. So if you want to know what, if you want to know the root mean square strain noise of the frequency band, integrate sum the squares and the AST over the band, then take the square root. There's a signal in these data for a moment. Let's ignore that and assume it's all noise. Okay. So there's a signal and we're trying to get it from the noise. Okay. Filter out the noise. So to do that, you can do mathematical manipulations of the data. Interpolations of the ASD computed above for whitening. Number of the sample fast Fourier transform. Sure. Here's an approximate smooth PSD. Dude, look at all this. Wow. If make plots, plot the ASDs with templates overlaid. Yeah, so I don't know what the effects of like doing mathematical manipulations like a Fourier transform actually have, so we have to learn that. Advanced LIGO strain data near GW150914. Note that we only plot data between 20 Hertz and 2000 Hertz. Okay. Below Fmin, the data is not properly calibrated. That's okay because the noise is so high below Fmin that LIGO cannot sense gravitational wave strain from astrophysical sources in that band. Below 20 Hertz, okay. Sample rate is 4096, 2 to the 12 Hertz, so the data cannot capture the frequency content above Nyquist frequency 2048 Hertz. That's okay because our events have detectable frequency content in the range given by F band, which is this range, I think. Defined above, the upper end will most always be Nyquist frequency. We set F max 2000, a bit below Nyquist. Okay, just 2048 is the higher end, but we just set it to 2000, which is whatever, that's fine, I guess. You can see strong spectral lines in the data. They're all of instrumental origin. Okay, strong spectral lines, okay. Some are engineered into the detectors, mirror suspension, resonances at around 500 Hertz. 500 Hertz. Okay. Sure. In harmonics calibration. Where's 500 hertz though? We have it's around here. This are they talking about? Suspension resonances at around 500 hertz in harmonics calibration lines. Control dither lines in some 16. We'll return to these later. You can't see the signal in this plot since it's relatively weak and less than a second long. While this plot averages over 32 seconds of data, so this plot is entirely dominated by instrumental noise. The smooth model is hard-coded and tuned by eye. It won't be right for arbitrary times. We'll only use it below for things that don't require much accuracy. Binary neutron star detection range. How long do we have left? Oh no. Read timed out. What do you mean? Why? If that happens again, then I don't know, but I mean, we gotta just try it again. Maybe the Wi-Fi broke or something and we lost connection to the download or something. I don't know. Read timed out. What the hell? Whatever. A standard metric that LIGO uses to evaluate sensitivity in our detectors based on detector noise, AST, and the BNS range. I mean, I'll just download it tomorrow if I have to go to school because the Wi-Fi is way better there. We take each neutron star in the BNS system to have a mass of 1.4 times the sun and negligible spin. Okay. Why do we just assume that all of them are 1.4 times? We're just assuming every binary neutron star is 1.4 times the sun. All right, sure. What? It's pretty random. GWS from binary neutron star mergers are like standard sirens. We know their amplitude at the source from theoretical calculations. Amplitude falls. Oh yeah, we have to learn about the Einstein equations too, because I don't really know anything about those. I know a little bit, but we're gonna have to learn about those. There's a lot to learn here, so after this tutorial, it gets pretty dense. I feel like. The amplitude falls off like 1 over r, so the amplitude at the detectors on Earth tell us how far away they are. This is great because it's hard in general to know the distance to astronomical sources. The amplitude at the source is computed in the post-Newtonian quadruple approximation. This is valid for the in-spiral phase only and is approximate at best. There is no simple expression for the post-in-spiral merger and ring-down phase. Okay. The amplitude source is computed in the post-Newtonian quadruple approximation. Oh, this is valid for the in-spiral phase only and approximate at best. There's no simple expression for the post-in-spiral merger and ring-down phase. So this won't work for high-mass binary black holes, which have a lot of signal strength in the post-in-spiral phase. So we don't have a good approximate. Okay, that's like related to the Einstein equations and the Newtonian equations. So they're using a post-Newtonian. Wait, what is this? In the post-Newtonian quadruple, they're using a quadruple approximation, which I don't really know what it is. During the in-spiral phase of the signal, but the in-spiral phase is like, I think the in-spiral phase is the part leading up to the merger between a binary neutron star merger and or a binary black hole merger. But once they're actually, I think the merger and ring down phase is, I think the in-spiral is leading up to it, and when they're literally about to merge, that's like the merger, and the ring down phase is maybe right after. I'm not positive, but they don't have good approximations for those, and then they lose some of the signal, I'm guessing, since they don't have anything good to measure those. It just kind of says that it's crap for measuring signal. So this won't work for high mass binary black holes, which have a lot of signal strength in the post and spiral phase. But in order to use them as standard sirens, we need to know the source direction and orientation relative to the director and its quadruple antenna pattern response to such signals. It is standard, if not trivial, computation to average. Oh God, I hate when people call things trivial. It's like nothing's trivial, dude. I guess. I mean, I don't know. Computation to average over all source directions and orientations. The average amplitude is 1 times maximum value. This calculation is described in Appendix D. Find chirp. An algorithm for detection of gravitational waves from inspiraling compact binaries. Okay. If BNS range is 1, choose detector noise power spectrums, frequencies, copy, get the frequency step size, F2 minus F1, constant speed of light, Newton's gravitational constant, 1 parsec, popular unit, astronomical distance, solar mass in seconds, isn't relativity fun, single detector SNR for detection above, noise background, conversion from maximum range horizon. Masses and solar masses, total mass, chirp mass. I don't really even know what half of this crap is. We integrate the signal up to the frequency. Okay, dude. So this is all just crap. I don't even know what it is. This is working better than last time. So BBH range is BNS range. Note that the mass is the source gravity and thus also gravitational. This is Python? Oh my god, man. This is pretty hard crap. Wait, so do we have this in our file? Yeah, so this is all in the file. Dude, damn, bro. Yeah, this got legit fast. Okay, we got to learn about Newtonian. We got to learn about the Einstein equations, and we have to learn a lot before we continue. So, you know, this is kind of just a rude awakening for how much we have to learn before we can even do these. And understand this tutorial, honestly. We'll compute the BBH range using a template with specific mass below, whitening from the ASD above. We can see that but that's what I said about LeetCode, and now I'm getting pretty good at that, so just gotta do it every week, just consistent, you know. From the ASD above, we can see the data are very strongly colored. Noise fluctuations are much larger at low and high frequencies, and near spectral lines reaching a roughly flat white minimum or band around 80 to 300. We can whiten the data, dividing it by noise amplitude spectrum in the Fourier domain, suppressing the extra noise at low frequencies. So this is just cleaning data. Okay, spectrograms. Now let's plot a short time frequency spectrogram along our event. Okay, so we have this is a spectrogram. Which I don't know what a spectrogram is, but now I do. This is one. Strain data. So let's see what this says. In the above spectrograms, you see a lot of excess power below 20 hertz. Yeah, sure. As well as spectral lines at 500, 1000, 1500. Yeah, sure. The lines at multiples of 500 are the harmonics of the violin modes of the fibers holding up mirrors of the advanced LIGO interferometers. So that's just how the interferometers were built. Now let's zoom in on where we think the signal is using the whitened data in hope of seeing a chirp. This is crazy how much you gotta do. So you zoom in using this code, Plot the whitening data. Yeah. This is the signal? I can't even see it. Loud, high SNR signals may be visible in these spectrograms. Compact object mergers show a characteristic chirp as the signal rises in frequency. If you can't see anything, try this by changing the event name in the first cell above. These are pictures from GW150914. Yeah, all I see is this nothing. Just this? Like this little thing right here? Like what is that though? The results of the full LIGO waveform template. The results of full LIGO Virgo analysis of the BBH event, binary black hole event, include a set of parameters that are consistent with a range of parameterized waveform templates. And the templates are generated from the Einstein equations. So they're consistent with one of the templates. Here we pick one to use for matched filtering. As noted above, so you use a template and then you do matched filtering with an actual signal. As noted above, the results won't be identical to what is in the LIGO Virgo paper, since we're skipping many subtleties such as combining many consistent templates. Okay, so they try a bunch of templates too. Properties from the waveform template. So this is a template. Yep, sure, and then they zoom in on it kind of. So how do they do matched filtering? It's right here. Okay. Matched filtering is the optimal way to know if a signal is buried in stationary Gaussian noise. It is the standard technique used by the gravitational wave community to find GW signals in compact binary mergers and noisy detector data. And we saw the noisy detector data. For some loud signals, it may be possible to see the signal in whitened data or spectrograms. On the other hand, low signal to noise ratio or signals which are long duration and time might not be visible even in the whitened data. LIGO scientists use match filtering to find such hidden signals. A match filter works by compressing the entire signal into one time bin. Okay, LIGO uses a rather elaborate software suite to match the data against a family of waveform signal templates to find the best match. The procedure helps optimally separate signals from instrumental noise and to infer parameters in the sources, masses, spins, sky location, orbit orientation, from the best matched template. So the template will have all the parameters and we match it to the template. A blind search requires us to search over many compact binary merger templates, 250K. God. So you do 250K template match filtering against 250K templates, okay, with different masses and spins, as well as over all times and detectors, and then requiring triggers coincident in time and templates between. It is extremely complex and computationally intensive search pipeline. So you use a supercomputer or clusters of nodes or something like that. Here we simplify things and only use one template, so because this is a tutorial, sure. The one identified in a full search as being good match to the data. Assuming the data around this event is fairly Gaussian and stationary, we'll use the simple method to identify the signal, matching the template in our 32 seconds of stretch of data. The peak in the SNR versus time is a single detector event trigger. This calculation is described by section 4, fine chirping algorithm detection of gravitational waves from spiraling compact binaries. Full search procedure is described in this. First results from the search for binary black hole coalescence with advanced LIGO. So this is match filtering. To calculate the PSD of the data, choose an overlap and a window that minimizes spectral leakage. Don't know what spectral leakage is, but that's fine. To find the complex template common to both detectors, so we get a template. We will record the time where the data match at the end of the template, so you get the times, length, sampling rate of the templates much match that of the data, so you get the sampling rate of the data and you apply it to the template to do the match filtering. Template.size, to remove effects at the beginning and the end of the data stretch, window the data. Okay, single tricky, template.size, alpha 1, okay, yep. So you just are fitting the template to the data, and then we're doing a plot. All right, let's see. H1 matched filter SNR around event. Okay, what is this? This is negative 0.15. So this is zoomed in. Okay, zoomed in. H1 whitened data around event. H1 whitened data, and then the template is the black line. That's so crazy. It's that similar? That's pretty crazy. H1 residual whitened data after subtracting template around event. So subtracting the template. I don't know why you do that. H1 AST template. I guess you just can mess around with them. L1 match filtering around the events. And then you got the template, subtract template. Wow. Notes on these results. We make use of only one template with a simple AST estimate. Full analysis produces a Bayesian posterior result using many nearby templates. It does a more careful job estimating the ASD and includes effects of uncertain calibration. As a result, our parameters, SNR masses, spins, somewhat different than you would see in our papers. We compute the effective distance. Is not an estimate for the actual luminosity distance, which depends on the source location and orbit orientation. These distances are non-zero redshift, so cosmological effects must be taken into account. Neglected here. Since we estimate the BH masses using the phase evolution of the waveform, which has been redshifted, the masses themselves are redshifted, the true source masses must be corrected. Yep. Make sound files. Make wave sound files from the filtered downsampled data. Okay, so do we have this in our... I don't even think this is in our file. Is it? Yeah, it is. Oh. So we write a wave file function to keep the data within. Yep. Wavefile.write. So we import wavefile from SciPy. Wavefile.write. Yep. Okay, listen to the whitened template. We can listen to it now. Holy crap. With good headphones, you might be able to hear a faint thump in the middle. That's our signal. Wow, that's the merger. That's weird, man. That is weird. That's weird, dude. Cool. Did this work? Oh, crap, I think it worked. So it actually might do all this stuff right now if we run this file. Did it create that wave file too? Yeah, it did. Oh, wow. Yeah, we ran the file. It worked perfectly. It didn't have any of the... you can download this file. Okay, cool. We can enhance this by increasing the frequency, this audio, The code below will shift the data up by 400 hertz. The resulting sound will be noticeably high pitched, easier to hear. Listen to the frequency. Sure. That's pretty cool. So they pitch shift it. Data segments as required above. LIGO strain time series data has gaps filled with NANDs when the detectors are not taking valid science quality data. Analyzing these data requires to loop over the segments, so quality of the data again. In the code below, we check many times event gaps in L1 data. You're welcome to repeat this with the H1 data file consists of 4,096 seconds of data. We also unpack injection. Yep, we got everything here. Comments on the sampling rate. LIGO data are acquired at 16,384 hertz. Here we've been working with data downsampled to 4096 hertz. Save the download time, disk space, and memory requirements. This is entirely sufficient for signals with no frequency content above 2048 hertz. Such signals from higher mass binary black hole systems the frequency at which a merger begins at the innermost stable circular orbit for equal mass spinless black holes is roughly 1557 Hertz times 2.8 over mass total, where 2.8 solar masses is the total mass canonical binary neutron star system. However, because we assume one was 1.4, so that was 2.8. Okay. If, however, you're interested in signals with the frequency content above 2048, you need data sampled at the full rates. Sure. Construct a CSV file containing the whitened data and template, and then you have a CSV file. Wrote whitened data to the CSV. You can download this file by clicking Juniper at the top left corner or using the data menu in Azure. Okay, that was a cool tutorial to kind of see how you would do digital signal processing with LIGO. You basically use a template that's already pre-generated using the Einstein equations. You're actually supposed to do matched filtering against 250,000 of the template gravitational wave events. That's a lot of time and computer power, so we obviously have to learn a lot more about this. A lot of the stuff in there was pretty high level, I think, and we're going to have to learn some digital signal processing and a little bit more of astrophysics, especially Einstein equations, before we go back in. So the next few videos, probably the next like 5 videos, are going to be digital signal processing and then astrophysics background research before we get into some actual digital signal processing in Python. And but I think we went through most of the tutorials, so that's just overall what the goal is, I guess. In the long run is to do a version of that that's more legit. And we're going to have to figure out how we're going to do that, especially when we need to match against 250,000 templates. I'm still in touch with the people from my summer research thing, though, so as I go through this, I might start contacting them again, and you know, we'll see where this takes us. So that was about an hour there. Went through that tutorial, saw a high-level overview of what we're going to keep doing here. And I'm going to end this video here, and we'll see where this takes us next time. So I'll see you guys later, and yeah, more LeetCode tomorrow. See you next time.